Go, 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 go. 7 years per hour here. Let's make it count.
1 hour. For the crew of Endurance, it was a frantic, terrifying hour in a world of impossible waves. But for the man they left behind in orbit, and for everyone on Earth, it was 7 years long. If you've seen that movie Interstellar, it's one of the most haunting ideas. We watch Cooper break down as he sees 23 years of his children's lives flash by in minutes. The emotional punch of that scene is just staggering. But it makes you wonder, is this just a powerful sci-fi or is there real physics behind it? Could 1 hour for you really cost 7 years for someone else? The answer, buried deep inside Einstein's wildest theories, is honestly more amazing than you would think. What happened on Miller's planet wasn't just Hollywood magic, it was a journey to absolute edge of what's physically possible. And today, we're going to break down exactly how that monster of a black hole, Gargantua, managed to steal 7 years for every single hour. Before we get into time-bending stuff, let's remember why they even went there. The crew of the Endurance wasn't on a casual road trip, it was on a mission. This mission was humanity's last shot. Back on Earth, the world was choking on dust. A global blight had wiped the crops and humanity was on the brink of starvation. They were a caretaking generation, just trying to survive, knowing their children might be last to starve. The planet was dying. The only hope wasn't to save Earth, but to leave it. In secret, what was left of NASA had a plan, the Lazarus mission. They'd form a wormhole near Saturn, a shortcut through space-time that seemed to be placed there by some benevolent, unknown intelligent. This was the doorway to a whole new galaxy. 12 astronauts had already gone through, each on a solo trip to check out a dozen of potentially habitable worlds. 3 of those missions sent back promising signals. These worlds were named Miller, Edmonds, and Mann, after the astronauts who had found them. The Endurance mission, with Cooper as a pilot, was the final gamble. Their job was to visit these 3 planets and find new home. But they also were in a race against time in more than one ways. The first and the most promising signal came from Miller's planet. It was an ocean world, showing signs of organic matter. But there was a catch. Miller's planet was orbiting dangerously close to Gargantua, a supermassive black hole. This was the source of a mission's biggest debate. The gravity was so strong it would literally warp time. The numbers were laid bare. For every hour they spent down on the planet, 7 years would pass by for everyone else. They had limited fuel, and a clock was ticking for all of humanity. Do they risk a quick, high-stake visit to Miller's or burn precious months flying to the next planet? With the promise of a perfect new home right there, they took the plunge. It was a decision that would cost them more than they could ever imagine. So what kind of a science could possibly demand such a devastating price? The story starts with a German patent clerk who completely changed how we see the universe. To get how time can be stolen, we have to forget the old idea of gravity. For more than 200 years, the world ran on Isaac Newton's definition. Gravity was a force. An apple falls because a force pulls it down. The Earth orbits Sun because a force holds it there. It's simple, it makes sense, and for the most of things, it works. But in the early 1990s, Albert Einstein came along with an idea that sounded like pure science fiction. In Einstein's universe, gravity isn't a force at all. It's just a side effect of shape of the universe. He told us to imagine the space and time as a single 4-dimensional medium, almost like a vast, slow-moving river. An object with a very little mass, like a small pebble, just flows along with the current. But a massive object, like the giant boulder, is so heavy it creates a depression in the riverbed. This depression forms a powerful whirlpool around it. Now, if a smaller object drifts near that whirlpool, it doesn't just float straight past, it gets caught in that swirling current and begins to circle the depression. To us, it looks like the boulder is pulling the object in, but there is no force. The object is just flowing the path of what the river is being redirected by. This is Einstein's vision of gravity. Massive objects like planets, stars aren't pulling on objects, they are just changing the flow of shape of space time around them. And everything else, moons, comets, people, we are all just being guided by the currents they create. The Earth isn't being pulled or attracted by Sun, it's following a massive current of space-time that Sun has created. It's constantly being swept inwards. But since it has enough forward momentum, it keeps missing the Sun. That's what an orbit is. The idea is so strange it needed proof. That proof came during a solar eclipse in 1919. Einstein predicted that Sun's mass would bend space-time so much that even light from distant stars passing by would have to follow the curve. During the eclipse, with the Sun's own light blocked, astronomers looked at the stars near the edge. And it was there. The position of the stars appeared to have shifted. The starlight had bent. Gravity could bend the light. This was the game changer. The universe wasn't static backdrop. It was a dynamic, flexible thing shaped by everything in it. And if space-time could be stretched, Einstein realized something even crazier must be true. Because space and time are locked together, and if you warp space, you have to warp time. And that's the secret to the 7 years lost on Miller's planet. The idea that time itself can slow down is probably the weirdest part of Einstein's theory, but it's a direct result of that curved space-time. If gravity is just a curvature of space-time, then stronger gravity means a deeper curve. And the deeper the curve, slower the time itself actually flows. Now it sounds like a metaphor, but it isn't. It's a real phenomenon called gravitational time dilation. Let's go back to our river. Imagine you have two identical synchronized clocks that are also waterproof. You let one float in the calm, slow-moving part of the river, far away from disruptions. You place the second clock deep inside the fast-moving whirlpool created by our giant boulder. According to general relativity, clock swirling rapidly in the whirlpool will tick slower than the one floating in the calm water. It's not the clock that's being damaged. The literal flow of time in that powerful current is slower compared to the spot with weaker gravity. If you pulled that clock out of the whirlpool, you'd find that less time had passed for it. It would actually be younger than the clock that stayed behind. This might sound like abstract theory, but you use it every single day. The GPS satellites orbiting Earth are in slightly weaker gravity than we are. Because of this, their onboard clocks run faster than ours by 38 microseconds every day. It's not much, but if engineers did not correct for this effect, your GPS would be off by about 10 kilometers every single day. We have to account for this time dilation just to find the nearest coffee shop. Now that's the effect from a planet size of Earth. Scale it up. A star causes even bigger effect. A super dense neutron star, still bigger. And at the most extreme end of physics, you have a black hole. A black hole is what you get when you cram so much of mass into such a tiny space that the dent in space-time is basically bottomless. It warps space-time so severely that past a certain point, the event horizon, nothing, not even light, can get out. As soon as you get closer to this event horizon, the time dilation effect grows exponentially. A minute for you could be an hour for someone far away. An hour for you could be a day or a year. The film illustrates this perfectly with sound. On Miller's planet, there's a slow, persistent ticking in the background. Each of those ticks represent one full day passing back on the Endurance. It's a terrifying reminder that every second they waste, they lose months of their lives and the lives of everyone they love. The crew knew this. They knew that going deep into the black hole's Gargantua gravity well, they are making a trade. Their time for the universe's time. The only question was, how extreme could that trade get? To get a ratio of 1 hour to roughly 7 years, they couldn't just visit any black hole. They needed a very special kind of a monster. The time dilation on Miller's planet is insane, a factor of about 60,000. Just hanging out near a black hole won't do that. If Gargantua were a simple non-spinning black hole or Schwarzschild black hole, the mission would have been impossible. For a black hole that's just sitting there, the last stable orbit a planet could have is still too far away to cause that much time dilation. Get any closer and you'd fall in. To get 1 hour equals 7 years effect, Miller's planet would have to be so close it would be torn apart. This is where the genius of Christopher Nolan and his science advisor, Nobel Prize winning physicist Kip Thorne, really shines. Nolan gave Thorne a story he wanted: an hour on planet equals 7 years outside. Thorne then had to figure out if any scenario consistent with physics could make that happen. And he found one. The key wasn't just the black hole's mass, it was its spin. Gargantua wasn't sitting still, it was a Kerr black hole, meaning it's spinning, and spinning incredibly fast at nearly the speed of light. That spin is the secret ingredient. A spinning black hole doesn't just create whirlpool in space-time, it actively churns it, forcing the river of space-time to spin violently along with it. Imagine our giant boulder isn't just sitting there, it's spinning incredibly fast. It wouldn't just create a whirlpool, it would whip the water into a furious vortex. This effect, known as frame dragging, completely changes the rules of orbital mechanics. This violent twisting of space actually allows for stable orbits much, much closer to the event horizon than otherwise would be possible. Kip Thorne calculated that because Gargantua's extreme spin, it was just marginally possible for a planet to exist in a stable orbit close enough to experience that massive time dilation. Miller's planet could whip around Gargantua, riding the currents of twisted spacetime without being gobbled up. And with that one detail, the numbers in the movie suddenly work. The crew is on the planet for 3 hours and 17 minutes, and when they get back to the Endurance, Romilly, who stayed behind, has aged 23 years, 4 months and 8 days. The math checks out. It's a gut-wrenching confirmation of the physics they bet against. What's even cooler is the dedication to get the visuals right. To create Gargantua, Kip Thorne gave the VFX team the actual equations from general relativity. The team then wrote brand new software to process them, with some frames taking 100 hours to render. This result was the first scientifically accurate simulation of what a black hole would look like up close. They discovered the gravity would bend light from the accretion disk, the ring of hot gas, into a strange and beautiful halo above, below, and in front of black hole's shadow. Years later, when astronomers with Event Horizon Telescope captured the first real image of black hole, people were stunned by how much it resembles the vision of Interstellar. The movie wasn't just entertaining, it was remarkably accurate. It showed that the terrifying time-stealing monster from the film was based on solid science. So, the time dilation math works. A supermassive, rapidly spinning black hole could theoretically have a planet orbiting close enough to make time pass 60,000 times slower. But could a planet like Miller's actually exist and support life? Well, this is where the needs of the story have to bend the rules of reality. The short answer is probably not. Let's start with those giant waves. In the movie, we see these giant-sized waves sweeping across the shallow oceans. They are caused by immense tidal force from Gargantua. Just like moon pulls on the ocean to create tides, Gargantua would pull on Miller's planet. But this force would be so much stronger on the side of the planet facing the black hole than on the far side. This difference would constantly stretch and squeeze the planet. Those kilometer-high waves are actually an understatement. The tidal forces would probably be so catastrophic they would heat up the planet enough to boil the oceans away, or even rip the planet apart entirely in a process rightly called as spaghettification. Even if the planet survived, Kip Thorne himself suggested it would be tidally locked, with one side always facing Gargantua. On a world like that, you wouldn't get traveling waves. The water would be pulled into one massive permanent bulge pointing at the black hole. Then there is the radiation. Gargantua is surrounded by accretion disk, a swirling vortex of superheated gas and shredded stars. In reality, this disk would be one of the most violent places in the universe, blasting out lethal amounts of X-rays and gamma rays that would sterilize any nearby planet. In his book, The Science of Interstellar, Thorne explains that for this story to work, they had to assume that the disk was old, thin, and anemic, usually cool. Well, it's not impossible, but it's extremely unlikely. And finally, there's the speed. To stay in that orbit, Miller's planet would have to be moving at an incredible velocity, likely over 99.9% the speed of light relative to the distant observer. At that speed, even hitting a stray dust particle would be like getting hit by an explosive shell. So while we can applaud the film for nailing the physics of time dilation, a habitable water-covered world like Miller's planet is almost certainly a fantasy. It's a perfect stage for the drama, but in our real-world universe, such a place would be hell. Interstellar is a story about love and survival, but it held together by one of the most mind-bending ideas in physics: time is relative. The trip to Miller's planet isn't just a clever plot point, it's a showcase for Einstein's general relativity pushed to its most dramatic and heartbreaking extreme. We have seen how a spinning supermassive black hole could warp space-time so much that 1 hour there could cost 7 years for everyone else. We have broken down how, with help from Kip Thorne, the filmmakers grounded this idea in real science. And while you probably couldn't find a habitable planet that kind of environment, the core concept, gravitational time dilation, is a fundamental truth of our universe. The movie uses science to ask the very human question: what would you sacrifice for a future? For Cooper, the answer was the time with his kids. It's that combination of cosmic science and raw emotion that makes Interstellar unforgettable. Thanks for watching.